to continue with 872b, which is, what was it again? 15 to 37 all. So yesterday you just worked on the first page. So I'll do one problem. Pick one that looks tough. Preferably an even 26. Okay, let me turn to it. So 26 says 4x squared minus 7x minus 3. Yeah. So if you look at 25, so the first fraction would be a over x plus 1, and then b over x minus 5, and then c over x minus 5 squared. Yes. And we're going to do the same thing on 26. So x plus 2 and x minus 1 squared. Now, how many unique factors do I have? No, factor. In the denominator, how many unique factors? 2. And one of the factors is squared, so how many partial fractions will there be? There will be 3. Are any of them quadratics? No. They're all linear. So this is going to decompose into a over x plus 2, and then plus b over x minus 1, plus c over x minus 1 squared. And then I multiply each of those by the common denominator, by all of these. But to save ourselves some time, we know that the first one, the x plus 2, is going to cancel x plus 2, so I really just need to do x minus 1 squared. And for b, one of the x minus 1s will cancel the x minus 1, so the b needs x plus 2 and x minus 1. And what about the c fraction? It just needs x plus 2. It already has the other two x minus 1s, so that will cancel both of those. So this gets x plus 2. So that's going to create a big, long equation. Do you remember how to square binomials in your head? It's going to be x squared minus 2x plus 1. So it'll be a x squared minus 2ax plus 1 times a, which is a. And then this one, can you multiply that in your head? It's going to be x squared plus x minus 2. So it'll be plus bx squared plus, it's 1x, which turns into bx, and then minus 2b plus cx plus 2. Justin, do you get that? So you set up the partial fractions, that's the easy part, and then every partial fraction gets multiplied by the common denominator. So the denominator that it already has is going to cancel, and the letter on top gets multiplied by the parts of the common denominator that it doesn't already contain. And then you create this big long equation which looks really messy, and it looks like we went from 1 variable to 4 variables. But if you look back at the original numerator, 4x squared can only be created using the x squareds in this big long thing. So 4x squared can only be created using ax squared plus bx squared. So ax squared plus bx squared plus no c's, there is no cx squared, is equal to, what was it, 4? 4x squared. And the other one, so 4x squared minus 7x minus, is it 2 or 3? 3. So this and this equal that. And then we do the same thing with the x's. Negative 2ax plus bx plus cx is equal to negative 7x. Maybe. Oh, we can't go down any further. So negative 2ax plus bx plus cx is equal to negative 7x. And then I look at the constants. A minus 2b plus 2c has to equal negative 3. So negative 2, nope, sorry, wrong line. So A minus 2b plus 2c is equal to negative 3. And then I realize I don't need any of the x's anyways. The only thing those x's did for me was tell me which ones to group together. So I can go through and I can get rid of the x's. Oh, that was a squared. Get rid of that. Get rid of that. And now I have a 3-variable system. Does that make sense, Justin? So once you multiply it all out, you set all of your x squareds into one equation, all of your x's into one equation, and all of your constants. If it's bigger than that, then you're going to have a cubic line, a quadratic line, a linear line, and a constant line. Just a, because it was x squared. And so really, when you write this system here, you don't even need to write the x's. You just say, okay, the top row is going to have all of my x squareds, so I'm going to use a, I'm going to use b, there is no c, and I'm going to use 4. You don't even need to write to x squared. The x squared tells you which ones go in the top equation, and the x's go in the bottom equation, and you don't need to write them. And then the constants go on the last row. So now you just take your calculator and plug those into a matrix. So this is a 3 by 4, 1, 1, 0, 4, negative 2, 1, 1, negative 7, 1, negative 2, 2, and negative 3. And then just do a reduced row echelon form. And I get the answer matrix 3, 1, negative 2. So that's my A, my B, and my C. So if I go back up here, I can erase all of this. So it's 3, 1, and negative 2. And those are the fractions that were used to create that original fraction. And once again, when you get to calculus, if you have multiple factors in the denominator, that makes calculus more difficult. It's doable usually, but it can be really, really complicated. If you only have one factor in the denominator, then calculus is much easier. So it's much simpler to treat each of these fractions separately than it is to try to do this entire fraction as a whole. And because they're equivalent, you're going to get the same answer in the end. Yes. So what that's saying is this here is one version of partial fractions that will add together to be this. Now, how many possibilities are there? There could be an infinite. There may have been an x plus 6 here and an x plus 6 here. And when I got to this point, I simplified it, and the x plus 6's canceled, and they went away, and we had no idea that they were there to begin with. So this is only one version that works. It happens to be the simplified version, which is the one we want. But, you know, there could have been a 30 there, and a 10 and a 20 there. And when you get to the end, you could have pulled a 10 out of everything. And there's no way to know. But the one we got ends up being the simplest version, which happens to be the most useful. All right, so go ahead and finish that one. Good luck.